Thanks. Okay, so it's a great pleasure to introduce Yunan Yang from ETH-ITS. Yunan received her PhD in mathematics under Bjorn Enquist from UT Austin. Following that, she was a postdoc at the Courant Institute at NYU. And she then joined ETH-ITS. Her current research focuses on computational math, especially numerical methods for inverse problems, PDE-constrained optimization, and computational optimal transport with applications to data science. It's a great pleasure to have her.
Yeah,
take it away. Thank you
for inviting me here. It's my first time in Minneapolis, and I'm happy to experience it in Minneapolis. It's nice. It's a very big city. Yeah, thank you for the organizers for having me in the data science seminar. Today, I'm going to talk about what I've been focusing on in the past 2 or 3 years. Is about the optimization component of PDE-based inverse problem or machine learning. Let's see. Okay, so I still have my most passion in inverse problem. So at the beginning, I need to explain, if you never heard about the word, inverse problem is always in contrast to forward problem. So it's just analogous verbs of each other. So for modeling perspective, or forward problem is more like a numerical solution to PDEs, or how to simulate a physical phenomenon as close as possible. You want to use a higher order method, for example. And in this framework, you are given everything you need, like say source, boundary condition, variable coefficient, as much as the physical parameters you need in the model. And you just want to simulate the process as close as possible. Like we want higher order methods, second orders, fourth order, or even like spectral method maybe give you arbitrary order. So that's study of the forward problem. But for the inverse process, is the opposite around. You don't see the data. Okay. In the inverse problem, you don't see the solution. You don't see the coefficient. You only see the data at some part of the boundary, or like you observe the data, but most of the time you observe part of the data, or even a function of the phenomenon. But you use those piece of information to help you to infer what exactly is the variable coefficient, or the source, or the boundary condition, or the initial condition that cause that. So it's a reverse part. If you think about PDE as an example in the mind, like you observe the solution, but now it's your time to decide what is the initial condition that caused that. And the inverse problem everywhere, some notable examples, including earthquake source. So when an earthquake happens, we observe shakes, and that is basically displacement in wave equation. And use that displacement, we want to relate what is the support of the source so that we can do things accordingly. And another inverse problem at a very big scale is this imaging the black hole. It's again, you have partial observations of the event horizon setup of some, like some stations, you observe the photons from the outer space, and you use that to have an algorithm to create an image of the black hole is another inverse problem. And the more common ones that most of us experience, including X-ray, CT, and ultrasound, the waves are recorded by those machines, and what they want to know is whether there's some broken bone or tumor inside the human body. So they are inverse problems. And more generally, nowadays, the model doesn't have to be PDE if we talk about inverse problems. So in my presentation, I will include a neural network also as one particular model that you can do inverse problem. But it's more like a general definition for inverse problem is that you have a model that is a neural network that you assume that is actually the model. And at the same time, you have data. So the data are like usually in pairs. If you are in supervised learning, you know the cat image and you know the label is cat. So you have a ton of those guys. I denote as some XY pairs. But what you want to know is the coefficient in the neural network. And that exactly is the training part of machine learning algorithm they focus on. They want to know the best weights and the biases in the neural network so that next time I give a new image that is not in the training, it's in the testing data, it can also give me cat or dog. So it's the inverse problem before the prediction part. In the sense you have a framework and you want to know the coefficient inside. So given these two type of inverse problems that I'm more familiar with, there are some pros and cons in terms of which is a good model. And I think there's a lot of discussions regarding whether you use a data-driven model or you use a PDE-based model. And I think on both sides, there's pros and cons. So let's say you are using a PDE model or ODE model, some physical-based model by first principle or experimental observations. Those are given. The good thing is they are given and they have been tested by physicists by like 100 years. And they are really trustworthy to be the modeling equation for wave phenomena or heat transfer. So you can just use it without any too much doubt on the model error, because if you have a wrong model, there's also a modeling error. But the bad thing is the difficulty of solving an inverse problem is always hand in hand with the forward problem. So almost everything we complain about how hard this inverse problem it is because the property of the forward problem that caused that. So that's the part. Like sometimes when we're working on inverse problem, we really hope we can change this elliptic equation to be less smoothing, but you cannot do that. It's elliptic in nature. But on the other hand, if you have the freedom to build a model, for example, some neural network, and you can manipulate the property of the forward model, for example, over-parameterized neural network, we know it has certain properties, or we know convolution neural network has certain properties. So you can really choose the model accordingly to match or to make the learning perspective easier, or make it adapt to your particular application and adapt to the accuracy of your particular application. But the nice thing is you do have a lot of freedom, like you can do extension, reduction, parameterization, even dropout, like those type of thing to change the model. But the trial and error is the con part, because you do not have a recipe. Most of the time, it's really just by practitioners is try and error, like try this and that, and finally we may find one. So it doesn't matter which model you use. So in my framework, in this talk, I'm not going to say which model is better, but let's say you fix the model and it is your most trustworthy neural network architecture, what's your most trustworthy PDE equation to really describe this phenomenon. The next thing we want to ask is, how can I find the coefficient? Given the data that a bunch of them we have available from all kind of sampling or observation or surveys, I want to find the best coefficient such that the model prediction is going to match the data. So then it comes to how we solve the inverse problem. And then in this framework, there's actually a lot of ways to do that. In general, I would say there's linear and nonlinear. Linear problem means the forward process, like given a parameter, the forward process that maps the parameter to the data is a linear relationship. For example, image denoising is a linear inverse problem. And when you are in the linear regime, how we solve a linear inverse problem involve direct method. For example, if you have A available to you, you can use Gaussian elimination. That's the direct method. Or iterative methods such as generalization or conjugate gradient descent or Jacobi iteration. Those are iterative methods in the classical sense of numerical linear algebra. So in this regime, we really need a lot of ideas from the category of numerical linear algebra and borrow all type of like fast and stable numerical algorithms. And the third method, more widely used to solve linear inverse problem, are optimization-based method. And then the most well-known will be least square minimization. Like we just reformulating the problem of solving AM equal to G as minimizing the difference between AM and G in most likely L2 sense. When it is nonlinear, you also have very similar analogous methods. So the first one is direct method. But in nonlinear inverse problem, you do not have this AM equal to something. So a lot of linear algebra technique cannot be used directly, but it can be used after you linearize this nonlinear forward problem. So for some people, if you really, or for some particular problem, if you know the inverse problem so well, you can actually cook up a direct method, which means you can have an inversion formula directly. But that needs a lot of assumption on the data and also require you know the problem very well. It's possible, but it's really challenging to construct an inverse formula that is a direct formula. Iterative method involve, for example, nonlinear generalization. And each time you do the nonlinear generalization, you basically is doing a linearization. And each small sub-iteration, you are solving a linear problem. So a lot of methods belong to this category. Or you can formulate solving f of m equal to g as a nonlinear fixed point iteration. And that's also something that can be used in many ways. And there's also acceleration methods such as Anderson acceleration to make it even converge faster. Okay, but the most common nonlinear inverse problem method to solve the nonlinear inverse problem is actually optimization method, as far as I can see, and that is the focus in today's talk. So when one reformulates this nonlinear inverse problem, f of m equal to g, into an optimization method, it is already a regularization or relaxation by itself, because you are dropping a lot of things down, rather than saying, I want these two to pointwisely match. In terms, g can be a function, so you really require a lot of things to match. You can say, oh, now I only want the difference between these two to be as small as possible. That drop a lot, and most of the time, under mild assumptions, you can have minimizer existence for sure. Although in the nonlinear problem, that by the equation alone, the existence of the solution is also questionable sometimes. So now we come to the optimization formulation, which is only one of the possible ways you can choose to solve a nonlinear inverse problem, and also linear inverse problem. So the key thing is that now you have an objective function, I call it J, and the J depends on the parameter M that you want to find. So M can be neural network weights, or can be the variable coefficient in your PDE, or can be the boundary condition or source term. And now this M is a data fitting term, because its goal is to just tell me how far away my simulated prediction from my reference data. So now usually it is you in a data fitting perspective, that is the difference between F and the G, with G denoted as the reference and F being the simulation. So it depends on your choice of parameter. So in this framework, I have a few more notations compared to the common one you see in those formulations. I want to bring your attention to particular two metric spaces. One metric space is what I refer as data metric space. So it is a space that they are measuring the difference of your data. It depends on, of course, which, what is the natural geometry or natural functional space your data should belong to. But here, not only I have a space, I also give it a metric. So DG is basically the metric between F and the G. Here you can also use divergence, which is not technically a metric. But here, I just in this talk, I restrict myself to a small subset. Another space that I think is more uncommon is a parameter space. So the parameter space is in which space you are looking for your parameter. So in PDEs, that makes a lot of sense to us, whether you are looking at a solution that is C infinity smooth, or you are looking at a solution that is L infinity. That is a big difference in terms of how strong you want your solution. You want it to be, your parameter to be infinitely differentiable, or you just happen to like it to be L infinite as long as it's bounded, you are happy. So that really changed the space like we are searching for. And I think that the bigger the space you are searching for the solution, the harder it is. So the smaller, the easier the problem. If it's finite dimensional space, then you can basically turn it in a finite dimensional problem. But in turn, on top of the space, you also have a metric. The reason we need a metric is quite important, because when solving such a minimization problem, in machine learning especially, people like to use gradient descent or even stochastic gradient descent. But as long as we have a gradient is the direction the objective function J increase as fast as possible. But in mathematics, you need a notion to quantify. You need something to quantify. What do we mean by as fast as possible? That's where this metric DM kick in. So the DM will basically clarify or quantify what do we mean by as fast as possible, so that you have a different DM, you have a different gradient. So this is two particular spaces, and I think they are very important, because when you change DG, which is a metric space for the data, you change the objective function, you have a different gradient. You also have a different optimization landscape. And when you change DM, you also have a different gradient, you have a different gradient flow or different trajectory, and that can also change a lot of things. So the main thing, the main message of my talk today is to emphasize how important that changing these two spaces can affect your optimization performance greatly. And I'm going to explain or demonstrate how you can change them in 5 different perspectives. And in a separate work, I also investigate that even in a classical inverse problem, you don't turn it into optimization, just into the f of m equal to d. Then how you choose the metric for the parameter and how you choose the metric for the data can also affect your stability. Sometimes it can be quantitative in the sense you have a different Lipschitz constant, but sometimes it can be qualitative in the sense you can change from Holder to Lipschitz. So that's a huge difference in stability. Okay, the first aspect I want to use to demonstrate the impact of these two matrix spaces is resolution analysis. So what do I mean that? Everything you can say most of the time has to be in a linear regime. So I use a linear inverse problem as an example. So here I'm trying to solve AM equal to G. So A is my linear operator, M is parameter, G is the data. But now I'm assuming that I actually do not have G. I only have noisy data, G delta. So that is the difficulty most of the time. If you have clean data, everything is in the perfect world. But if you have noise, that's where the overfitting can occur. So I specify which matrix space I'm in. M is in H beta. So H beta is a Sobolev space, W2 beta. And the beta is some integer, so it can be positive, negative, or 0. And I also have assumption on my forward operator. And earlier I mentioned the difficulty of the inverse problem always comes from the forward problem. So here I say the forward problem is smoothing in nature. In the sense, it will turn something H beta to H alpha plus beta. So alpha is positive, so you basically gain alpha orders of derivative in your solution. So that is a smoothing operator. But it's exactly this alpha makes things really difficult in inverse problem. I just give a very simple example. We have Fourier transform, we have inverse Fourier transform, but we never consider inverse Fourier transform as an inverse problem. The reason is alpha in that case is 0 because of Parseval identity. You don't lose anything. It's L2 to L2. So you don't lose anything. That's why the inverse problem is so nice and there's nothing to worry about. But as long as alpha is larger than 0, you are in a trouble in the sense that you are always losing something in what you observe. You lose, let's say you have a rough coefficient, but you only observe smooth things. Then how can you reconstruct the rough coefficient, especially if there's noise? So for wave for redown transform, alpha is about a half. For wave, it's about 1. But for Cadorans problem, which is elliptic inverse problem, alpha is 2. So alpha is Cadorans problem is usually the worst stability one in our concept of PDE-based inverse problem. Okay, now the third assumption is on the data. And since A will turn H beta to H alpha plus beta, I can just put the data in any space that it belongs to. So as long as S is smaller or equal to alpha plus beta, I'm fine because I'm in a matrix space that this data will belong to, because smaller HS usually means a bigger space. So this is where, as a user, you do have a choice. You can choose alpha plus beta if you think it's optimal, but you can use the weaker norm, which the data misfit is still finite. So this is the S is where you can choose either bigger or smaller, and you can see next that you actually make a difference in terms of choice of S. So in Sobolev HS norm, there's multiple definitions, and one of the most convenient one is to take a Fourier transform. So that's where you can see S equal to 0 is a special case. So when S equal to 0, H0 is basically L2 norm in the sense that weight is 1 homogeneously for every frequencies. But if S is bigger than 0, let's say 1, then that means this weight is much bigger in higher frequency compared to lower frequency, in the sense that H1 norm will focus a lot more on the higher frequency and the lower frequency. As an objective function, it already have an implicit bias in the sense what Fourier component I care more, right? So when S is negative, it's the other way around. You will have much bigger weight on the lower frequency component of the residual compared to the higher frequency. So as using a negative norm, it means you really care about smooth things, and you don't care that much about the higher oscillatory stuff. And then next is a theorem stating, it's a theorem that I assume I really have an inverse operator I can directly apply. But because my forward problem is so smoothing, it's very ill-conditioned to have the full inverse, because there's a smaller singular values and I don't really want to invert that. So what we do is we truncate. You choose a frequency cutoff up to one point that you think, oh, I'm not going to, it's like a low rank approximation. In the sense, if it's too small in the singular value, I'm just going to ignore that. And I give up the fact that I may recover that. So you take it as 0. But when the singular value are relatively larger, I will take it as the true inverse of the forward operator. So there's a cutoff. And once I define the inverse operator, I apply it to my noisy data. The reason we have a cutoff is all because we have a noisy data. We don't want to too much amplify that. then you have a reconstruction, which is based on this noise. Then we can ask the question, what is the difference between my reconstruction versus the ground truth? And then on the right-hand side, you can see it depends on the three important parameters I mentioned, alpha, beta, and S. Just to recall, beta is the space I'm living in, alpha is how smoothing A is, and S is our choice. So you clearly can see the right-hand side, how small it can be depends on the S. And if you balance the two terms, you can see the optimal resolution depends on delta to the power of 1 over alpha plus beta minus S. So how you choose S can affect how fine or what is the higher resolution you can see in the solution. So that's in the resolution analysis. Choosing different S, it depends on the optimal you can see in terms of the inverse problem parameter. Okay, the second part is by choosing different metric spaces, you can be more robust to noise or less robust to noise. And in this entire framework, I do not talk about regularization because I know regularization can also help us to mitigate noise in the data. But if I bring that into the image, it will be a little bit confusing because you don't know whether the effect comes from the objective function or the data metric or come from the regularization. So there's no regularization. But I want to say, even if there's no regularization, just by your own choice of the objective function, you can also achieve like a preconditioning effect in terms of being insensitive to noise. And this is, again, our HS norm that we saw in the previous slides. But now I'm defining it in a discrete setting. So because once in discrete setting, I can just do gradient update. So in discrete setting, the Fourier transform part can be absorbed into this operator PS. And the PS is actually a discretization of identity minus Laplacian to the power S. So that's also directly come from the definition of HS norm. And now, if we write it down, the HS norm in this way, some people may recognize it's in the form of weighted least square. After discretization, it's indeed a weighted least square, although in the continuous setup, it's a different functional space. But this weight matrix PS is hand in hand with the choice of the HS norm. So you don't now have a lot of choice or a lot of freedom in terms of how it should look like, but it was based on the HS norm. And now we are going to do gradient descent, and the objective function is written here. We can very easily to see the gradient will be A transpose PS times the residual. So different from the normal, the standard normal equation gradient, which this PS is identity, we have this weighting matrix in front of the residual. And when we do a one step of gradient descent, tau is a step size, so mn minus tau times the gradient. You can see it will be a linear combination of the current iteration and the data. So data G delta per with PS and the back propagating. So this is where you can see different travel PS can control how much of the noise in the data propagate into my next iteration. So next iteration have contribution from the previous iteration, but also have the contribution from the noise. So if I choose an operator PS that is more insensitive to the noise, it's more like a protection layer that stops the delta, the noise component of the data, to back propagating into my parameter. So then the different of PS, you can make it more robust noise or less robust noise. Just as an example, this is a 1D denoising example in the sense A is identity. So we have noisy input, and the true ground truth should be just white and black piecewise constant. And with a little bit of noise, you can see the performance of different choice of S. If I use L2, least square minimization is well known, we will have overfitting. The noise will be in the parameter. So we have something even noisier than the input. But by choosing different weaker norms, you can see the back propagating of the noise is gradually mitigated. And the best performance, I would say, is about S equal to negative 0.5. And that's because the weaker norm focuses more on the low frequency of the residual. And that's why the high frequency noise gets damped. So it doesn't kick in into your solution. And similarly, when you are in the second row, the noise is stronger. And when the noise is stronger, the S equal to negative 0.5 is not necessarily the best, the choice of S. Is actually S equal to -1, at least in these 5 choices, is the one that reduces the noise even more. And again, it's because the choice of S, it really depends on the noise power in G delta. So the best PS will be the one that exactly just get rid of G delta. So, and in another framework, you can also do a similar analysis in feature regression, because in machine learning, there's a particular problem called feature regression. It can be random feature or some standard features that we like. So even in this framework, you can also carry out similar analysis. So classical will be on weighted least square minimization. So in this paper by Xie and Richard Warsaw, some group in UTL, I know, they propose a method that, how about I reparameterize W, reparameterize theta, so that is a change of variable. So instead of finding theta, I'm finding this matrix multiply W. So it's a change of variable, but as a result, you are finding W as your inverse problem target. And correspondingly, you are changing the forward problem. The forward problem originally was psi as a feature matrix acting as a coefficient. But after the change of variable, your forward problem is psi times this matrix. In the sense that all the bad things about the forward problem, you can try to remedy that by having this matrix. But this is in the discretized setting. In the continuous setting, what we are doing now is exactly change the matrix space where you are circling the parameter. Instead of finding theta, you are finding the parameter in this space. And because of the propagating, so it's actually equivalent to changing the forward problem. So what we proposed is that once we see this is very close to what we had in mind, not only you can change the parameter, which is one side of paying attention to our matrix space, you can also pay attention to the data matrix space by applying this matrix in front of the whole residual. So these two matrices actually play very different roles. You can refer to this paper in detail to see how, especially when psi is underdetermined or overdetermined, and also depends on y has noise or not. They are not playing exactly the same role, although sometimes they are equivalent. So these two matrices also change our generalization error, because once we are in a machine learning setup, generalization error will be the criteria to see whether one framework is better than the other. So you can also see that generalization error will be better if you choose alpha and beta correspondingly matching the property of the feature matrix and also the noise power of the data. And earlier I have been talking about strong, higher frequency noise and a weaker norm, but reverse wise it also holds true. Let's say you have low frequency noise. It's not very common, but in some application you can indeed find it. You have a low frequency noise, and the noise in that framework is also a denoising procedure. I want to remove this artificial illumination come from some imaging procedure. And in order to remove the lower frequency noise, you can see that it's actually the stronger norm will do better, because H1, H2, higher, stronger HS norms, they are more focusing on the higher frequency component, and higher frequency component in this application is exactly what I need. I want to know the fine structures, and I do not want to see those bright illumination, which is noise. So you can see HS norm is performing the best, give you the highest PSNR in this framework. So both ways can go, but that indeed require you to know your noise a little bit well. You know what you are dealing with is low frequency or high frequency. And here I want to comment a little bit on the Wasserstein distance, especially quadratic Wasserstein metric. It has been used in inverse problem and also in machine learning as a measure of comparing the two distributions. So Wasserstein metric has a natural low frequency smoothing effect thanks to its relationship to H-1 norm. So earlier we see H-1 norm is kind of robust to noise because it has higher weight on the low frequency and a smaller weight on the higher frequency. But now, based on these two theorems, two results from these two separate papers, you can see the quadratic Wasserstein distance is actually as smooth as H-1 norm. The first result is asymptotic analysis in the sense that if you are compare mu and a small perturbation of mu, then it's asymptotically first order up to first order that it is the differences H-1 weighted on mu. So this is one result. Another result is come relatively recently in the sense that if you have F and G, which are the densities of two probability measures, as long as they are bounded away above and below by two constants, it doesn't matter, they have to be close, but as long as they are bounded away and below by two constants, then it's exactly equivalent, linear equivalent to H-1 semi-norm. So if you draw this functional space graph, like to put all the functional space we know in some several dimensional space. I saw that in Terry-Tau's blog. Then if you put the Wasserstein somewhere, that will be right next to H-1. So that's basically I want to say in this slide. And we know that, and it's not surprising if I use the Wasserstein distance to match the difference between my simulated data and the noisy reference data is very robust. So here I give you an example. I have the clean wavelet or clean wave field, one slice of it. In the sense I fix X, just look at the time series. So the black one is real signal, but now I pollute it by some correlated noise. Now it becomes the blue signal. It looks really bad and give me really bad SNR. So it's not a good noise at all. It's overshadowed the data. But it does have one property. The property is this noise is high frequency in terms of how I add it. It's really, really dense in the sense that the oscillation happen a lot. And also the fact that it's mean zero. Okay. Now, if I do optimization with this wave inversion framework, so you can see the velocity or which the parameter reconstruction get updated iteration by iteration. And also the data on the right-hand side is changing a little bit iteration by iteration. The blue one doesn't change because the blue one, as you saw earlier, is my noisy reference, but the black one get updated. So after exactly 87 iterations, the optimization stopped because the gradient is zero. And also on the left-hand side, we reconstruct the classical Marmousi benchmark in this community. So it's very close to the ground truth. So now you may be curious why it stopped, because on the right-hand side, it doesn't look like they are the same, but it doesn't look the same because by our eyeball norm, or by our normal way of perception of the difference, or it doesn't look the same in the L2 norm at all, or any LP norm, but it does look the same under the Wasserstein distance, because optimal transport has its unique way of comparing two signals. It's always the amount you move multiply the distance you move. So here, the amount we need to move in vertical direction mismatch is very high, it's order 1. But because it's dense, the horizontal direction you need to move is 1/n. So square it is 1/n square. So in general, just the difference between the black and the blue is only order of 1/n. And n here is like 1,000. That's why for the Wasserstein distance, there's almost nothing left. Okay. The third aspect I want to emphasize about the change of metric space is changing the spectral property. And this is probably the only super relevant machine learning example in this talk. So I'm considered a two-layer neural network, and one of the layers is extremely over-parameterized. So there has been a lot of research. I cited only a few here, but there's a lot of research along this direction to analyze what the dynamics and also what's special property. One of the property people realize is that if the neural network is extremely wide, in the sense extremely over-parameterized, you do observe a low frequency bias in terms of data matching. So what does that mean? It means you have a very oscillatory target function on the background. So you want to learn this function and you parameterize everything by neural network. So now you start with this blue, the green one is iteration 100. And then when you have iteration 1000, what you learn is a little bit more oscillatory. Iteration 10,000 is actually more oscillatory. And finally, iteration 80,000, it matches. So what makes people feel interesting is now the fact that you can match the data. I think nowadays you can match the data as long as optimization is good enough. But the fact that there's an order, it's a very obvious order. The order is from low frequency components, finally to higher frequency component. And the order is actually what decide many of the PDEs we analyze, like elliptic, hyperbolic, etc. So when people see that, people kind of see things we are more familiar with. So people want to do rigorous math to understand this phenomenon. So how do they do math about this? Of course, you have to throw in a lot of assumptions, assuming that you have this objective function and you discretize, there's a continuous setup, which means the distribution of the data is this mu. So you, after like discretize or sample the mu, you get this Monte Carlo sum on the right-hand side. So that's your discrete object function. This is your continuous objective function. And next, if I can do gradient descent and have a lot of assumptions in it, in the sense that it's almost like a linear regime, I can understand everything by its neural tangent kernel. Then I can understand its spectrum. So y minus uk, y is the reference data. UK is basically the case iteration what the neural network gives you. So y minus uk is your residual, and we want the residual here to be as small as possible to go to 0. But if you do some expansion, you realize how it goes to 0 is dictated by this particular matrix. And this matrix is neural tangent kernel, but this neural tangent kernel matrix evaluated at your data points. That's why it comes from the kernel to a matrix. So the neural tangent kernel is literally, I would say, some tensor product between the Jacobian. So this is Jacobian of the neural network. It's tensor product with each other, which itself, and then you get this neural tangent kernel matrix. And so basically, based on this equation, as long as I know the spectral property of H infinity, I would know the order of the learning, because this is how we actually conduct power iteration convergence to find the dominant eigenvalue. It's the same type of analysis. So, but we need to know what is the biggest eigenvalue of H infinity and the corresponding eigenvectors. So that's the next way to go. So that's where people have to throw in a lot of assumptions, because for a general neural network, it's very hard to know what is the H infinity analytically, what eigenvalue and eigenvectors. But that wouldn't be a too hard problem if you assume if it's uniformly distributed, and you assume that the activation function is, I think most of them, at least for ReLU, you have analytic formula. But if it's not ReLU, you also have approximating formula. Sigmoid, people already understand them very well. So yeah, so the short answer is using this von Kaki formula with the assumption that data are uniform distributed on a sphere, then you know the eigenfunctions are exactly spherical harmonics. So what is spherical harmonics? It's more or less like a Fourier basis generalized to a sphere. So you still have degrees from lower degree L equal to 1, 2, 3, 4, 5. It's the same as you have frequency 1, 2, 3, 4, 5. So the higher the degree, the more solitary it is. So it's just a direct counterpart. But this does tell you the biggest eigenvalue of H infinity is the smallest L, which means the smooth coefficient or smooth spherical harmonics have the biggest eigenvalue. And that is why you can see why here, because whoever have the smallest weight will converge the fast. So when we know when L is small, let's say L equal to 1, mu L is the biggest. So 1 minus this thing is going to be the smallest. So the smoothest component YL is a projection onto the spherical harmonic smooth is a projection onto that particular basis. So you know this will converge the fastest. So that's how people actually finally conclude smooth to oscillatory come from the spectral property of this matrix H infinity. Again, you need a lot of assumptions. So one of the assumptions that I feel could be relaxed a little bit is the fact that data need to be uniformly over the entire sphere. Most of the time, we do not have control over whether the data is uniform or not. So one of the things that we try to relax to understand a little bit more is to see if I have non-uniform data, which means all the analysis earlier may not hold, how can I still understand the frequency biasing in neural network? Or how can I still achieve frequency biasing in neural network if I have non-uniform data? So when we were doing that, we realized there's two objective functions as per user's choice. You can think your objective function in the continuous setup to be mu weighted integral, which means d mu x, mu is the distribution of x. Or it can be Lebesgue measure integral, which is the most standard integral. So these two choices up to you, because if you can minimize all of them to be 0, I think there's some equivalent between these two if you have assumptions on mu. But after discretizing, they have different forms. One is a very simple 1 over n Monte Carlo sum, which 1 over n is your quadrature weight, is a Monte Carlo quadrature weight. Or you have a more careful quadrature weight called Ci. In case you wanted the discrete sum to equal to the continuous integral. As all of us are numerical analysts in this paper, so for us, whenever this tilde need to hold, really you need to be careful with the quadrature weight, otherwise it can be huge. Okay, once we have these two, then you may wonder which one I should choose, which one give me a better performance, or like many things that you care about. So that's the entire analysis hold on to. So von Kaki formula as a formula that is used in spherical harmonics a lot only works for Lebesgue measure integral. If the von Kaki if your integral is not Lebesgue measure, the von Kaki formula cannot give you the eigenvalue and eigenfunctions anymore. So you actually do not know what is exactly happening in your H infinity. But as long as it's the big matter integral, you do know what is happening. So that's the beauty, and that's why we advocate for a free tilt. So I'm just going to summarize the main result in the paper is that you actually lose frequency biasing if mu is no longer uniform. When mu is not uniform, there's a difference between these two. So you don't have this clear low frequency to high frequency transition, because not only you cannot analyze it, but also I don't think it exists, it's true anymore. But if you use the second one, the tilde one, as your objective function, you pay a little bit more. Where you pay, because you no longer have this 1/n weight as just like you don't even have to think about it. You do need a quadrature weight that you need to compute by certain ways, depending on how high order you want. But if you stick to this discrete level, you have this continuous analog, then you will still have frequency bias up to quadrature errors. So as a demonstration, you can see the next slides. The solid ones are the phi, the one that corresponding to the first one that is, corresponding to 1/n rate. I think it's not, okay. But the tilde, the dot one corresponds to tilde. Blue is low frequency, red is middle, and yellow is high. So you can see for when you have the tilde one, you clearly have scale separation. Low frequency convert first, number of iteration, error, and then middle frequency and high frequency. But when you use phi, the original one, when you have extremely non-uniform data, they don't basically just blend in. You don't see the frequency gap anymore. So that's a demonstration. You actually lose frequency bias, this smoothing property of over-parameterized neural network if your data is non-uniform. And another thing that we have been talking about HS a lot so far. So you can also say why you have to be L2 based measure, well, L2 based norm, that can be weighted L2 or L2. That's basically the difference between phi and phi tilde. You can also say, like, I'm going to talk about HS norm, and similarly, you will have this weighting matrix after discretization in the middle between the residual. So this is what I like the most, because now you can even see the frequency, like this residual decay, not only is dictated by the eigenvalues and eigenfunction or eigenvectors of this neural tangent kernel, it also has this blue factor kick in, and that factor come from your choice of objective function. So once have this factor in it, then the order that we say earlier, like a smooth will first, the oscillator will be later, will be reordered, because it will be mu times this weight that dictates your order. So you will see how this actually can effectively change your frequency bias. So this is the part I like the most in this presentation. So when s equal to 0, you are in L2 regime. So this is a standard analysis. And you can see there's a frequency bias. Blue is a low frequency, red is a high frequency, and there's a transition who converts first. So it's after fixed number of epochs, the blue one will be 1e-3, but the red one is 1e-1. So there is an order, right? But this is the order that is only in L2 alone. As a user, you can actually change it. You can either go this direction to the negative direction, in the sense that you use a weaker norm as your objective function, and you are amplifying that difference, right? You can make the low frequency and the high frequency difference to be much bigger, like the difference is much bigger. So you have much more bias towards the low frequency compared to the higher frequency. Or if you are not happy with the smoothing property of a neural network, which is the case, because if there's smoothing, you have slow convergence for the higher frequency. And that's probably the case when you learn, like the Burgers equation solution. It takes very long because Burgers equation solution have high frequency in it. So if you are unhappy with neural networks low frequency bias, you can also try to mitigate it or just to neutralize it by going to the other direction, to the s equal to s being positive. Then you are basically bridging the gap between these two. And at one point, especially for this example, at this point, you don't have any bias anymore. They convert equally the same. So there's no bias in error, but it's all more or less like possible identity perspective. Error frequency is the same. And you can even reverse that. That's where the rainbow gets reversed. That when S is so big, the higher frequency will convert faster. The lower frequency will be on the top of the line. So what I try to demonstrate in this slide is to say the bias or the spectral property, indeed, you are given this over-parameterized neural network. On one hand, that is the natural property. But if you use an objective function, as you can see here, your choice of objective function also affects the property at least affect the spectral property of the iterative optimization algorithm. And you can have a lot of leverage to change how your optimization algorithm performs. And again, those are all users' choice. And this is just a simple example to show you have blurred image, then you can choose different, this is autoencoder, so it's a neural network-based model rather than identity operator as the model. So you can see different S12 or S also make a difference. When you have low frequency, a stronger norm is better. When you have high frequency, weaker norm is better. So it's a demonstration of a concept. Okay, the fourth aspect is improving the optimization landscape. I think that is relatively more straightforward. When you have an objective function, which is a data fitting term between f and g, you change, line choice will be L2 norm, another choice will be KL divergence, the third choice will be Wasserstein distance, the other one will be maybe a chi-square distance or some other divergence over there. So each time you change the objective function, you are changing the optimization landscape. So one objective function can be convex, another can be non-convex. So that really changes your optimization performance really quantitatively and qualitatively. So here I give a very simple example that I'm most familiar with. So in waves, we always just compare like a one wave versus translated version. So on the bottom, there are the demonstration of the two signals. I have the blue signal, which is fixed, is probably my reference, but I guess some velocity parameter wrong. I have a red signal, which is purely translation of the blue one. They are not the same, and that can come from the wrong velocity in the wave equation. Now I want to compare their differences. And if I compare these two, in the L2 norm as a function of the shift, this is the optimization landscape you can see. It's really non-convex, and to make things worse, if these two support of the two signals are really far apart from each other, the L2 norm will remain constant because L2 doesn't really see this thing anymore, right? It's a very local metric. But on the other hand, if you use the Wasserstein distance as an objective function, you can turn something really nasty to a global convex optimization. That only works for a single variable, as you can extend it to more variables, but it may not be true in higher dimension, but what will be true, you always will have a bigger basin of attraction, like a bigger in the sense of wider. So this is much wider compared to this one, for example. And also, very interestingly, this will be corresponding to the frequency of the signal. So right now it's this frequency. So basically how wide this global background attraction for L2 is corresponding to the frequency of the wavelet. And in larger scale, as I said, in this example, I have millions of variables. So the unknown is no longer a simple shift. It has a million variables. I cannot prove global convexity, and I don't think it's really even true necessarily. But what I can see is starting from the same initial guess, with everything else being exactly the same optimization algorithm, the same way to choose a step, everything being the same. Then these two objective functions, the left is L2 norm as objective function, the right is the Wasserstein distance as objective function. They have very different trajectory, and clearly one trajectory is better than the other. Even if you don't know the Mamouzi ground truth that I just saw presented earlier, even if you don't know what will be the parameter, since in realistic situation you do not know the ground truth, but you just look at the residual. Since this is a data fitting approach, so whoever fits the data will be the winner. So data residual is actually a very good characterization of the method, and that is always available to you. So you see the data residual of the Wasserstein, it's almost gone. There's some left over, there are higher frequencies, but it's much better than what we see on the left. And the residual no longer change. In the L2, that's a sign that it gets stuck at local minimum. Yeah. And yes, here. Okay, so that's another perspective I have on local minima. Since if we are dealing with 1 million variables in your optimization problem, proving something is convex or not, that is out of reach. But you can use something as your motivation to choose one objective function versus the other. So now I have to start with when we get stuck. When we get stuck, most of the time, gradient is 0. So when gradient is 0, especially in this data fitting approach, like you observe data, but data actually depend on the parameter, you have a chain rule, you have 2 layers. So your gradient is a combination of 2 parts. First off is objective function feature derivative with respect to the data. Then the data feature derivative with respect to the parameter. So we often call this thing as Jacobian. So your gradient in all of the aforementioned problems have these two parts. And yeah, another way to say your gradient, true gradient, is actually your feature derivative, data feature derivative, projected onto the space spanned by the Jacobian. So whenever the gradient is 0, it means there are several things it can make it 0, but dJdF, which is the feature derivative of the data, actually is never 0. L2 norm's feature derivative is f minus g. So if f minus g is 0, I'm really happy because I feed the data. But most of the time when you stack, this is not 0. You can see in the previous slide, there's huge misfit. Okay, the Jacobian in finite dimensional, I think the Jacobian is usually well posed in the sense you are actually not in a really bad location. We can assume that the Jacobian in finite dimensional is non-zero, which means it has finite number of ranks. Then when you project dJdF onto this Jacobian, the only left possibility for the gradient to be 0 is the projection being 0. So that means, okay, my data want to go this way, but there's no feasible parameter that allow my data to go that way. So then that's where you can change your objective function to make sure that the objective function is aligned with things like in the Jacobian they want to do. So for example, wave as example, wave like to do things horizontally because it propagate along the characteristics. The Wasserstein distance will be a good choice because Wasserstein also like to compare things along the characteristic. It like to compare translation. That's why for the same situation, the Wasserstein projection onto the Jacobian is non-zero, so we don't get stuck. So that could be used as a motivation, and vice versa. If you do have the freedom to choose your model, if you don't change this part, you can also change your Jacobian. But this is a luxury for PDE-based methods. But it could be better for machine learning-based model since you can't really change what your model is. And that's why I think the power of using, for example, optimal transport-based metric in inverse problem is way beyond hyperbolic, because you do not need the equation or the application to be hyperbolic. You only need the phenomenon or the Jacobian or the continuous dependence, depending on how you call it, between your parameter to your data to be hyperbolic phenomenon. So for example, deconvolution from highly localized sources give you a hyperbolic phenomenon, or deconvolution from diffuse environment, or reconstruct from projections, or even some people recently use Wasserstein distance in Cadron's problem. So they found a setup that actually, although the PDE itself is elliptic, but the relationship between my parameter to my data is hyperbolic in nature, in the sense that there's transport, translation, like dilation. This is global hyperbolic phenomenon. Then using Wasserstein, you will gain benefits. Okay, now we come to the last part to show that actually the change of metric will be beneficial. And unfortunately, I have been focusing a lot on the data metric in the previous part. So this one is about the metric for the parameter space. So just recall our particular setup, and also where I try to emphasize, you have a metric to measure the data misfit. You also have a metric space to characterize what is your gradient. And this is actually, I would like to present because this will show you exactly how the gradient will be based on your particular choice of DM. So the first part is it, just let me take a step back. So in a continuous setup, you can use gradient method, you do have a gradient flow, and the gradient flow is a PDE. But how to solve the gradient flow? One of the numerical scheme is implicit Euler. And when you use implicit Euler, you can write it down that scheme to be equation 5. So it's discretization of the gradient flow in implicit Euler perspective. I like this because it shows where the metric space kick in. So you can see how you choose this DM, decide how do you find the next iteration given the current iteration. And then different DM will, of course, give you different next iteration and affect your trajectory. And there's another gradient descent called natural gradient descent. So the natural gradient descent is one step further regarding how you decide the next iteration. So natural gradient descent is I'm no longer in the metric space for the parameter. So earlier I was still trying to find the closest next iteration, but the closeness is measured by the metric on the parameter space. But natural gradient descent is lifting the parameter space to the data. And then say, I'm trying to find the closest in M by lifting it to the data space and finding the next iteration. So people call it natural gradient descent. It's from machine learning community. And that's exactly in machine learning. You have all kind of model. You can use fully connected convolution or like naive Bayesian, those type of framework. But different, then there's no well-defined metric space, but there's always well-defined data space, because when you lift, that's exactly what you observe. So they think it's more reasonable for me to just consider the next iteration in data space. And indeed, you get a lot of benefit by using natural gradient descent. For example, the decay in objective function is independent of your parameterization. Okay, so this is basically where I try to say the gradient is now the derivative. So one quick example is you can have the objective function being L2. So the metric space are both L2, but the parameter space, one is L2, another is H1. So that's where you change DM. But when you change DM, you have two different gradient flow PDE. And if this A is particular grad operator, then you will, for this particular application of the gradient flow, like with A being gradient operator, then one of them give you a parabolic PDE, but the other is linear. So the second one is the best because the Lipschitz constant is 1, and they give you the fastest convergence independent of the grade size. So this is achieved by different metric space to talk about the gradient flow. And there's a trade-off. It's not like, that's why I learned this from Mike Chogov's work. And also he said this Nesterov tutorial. You can always play around this, not only in inverse problem, but even in convex optimization. But there is a trade-off. The Lipschitz constant and the error is always go inverse proportional. So if you have a Lipschitz constant that is small, the error here will be huge, and vice versa. So you may have to consider which one is best for your choice. And in Matt's work of this paper, he chose the one that is just close enough so that you get great discretization independence. So that is a qualitative difference in the sense you can actually gain something this global unconditional Lipschitz versus that is not even Lipschitz. Gradient operator is not even compact. You don't have Lipschitzness. You only have Lipschitz after discretization. So for numerical solution to PDEs, I would like to work with the second much better than the first one. So this is a quantitative difference using different metric space for the parameter. You can, like after the same number of iterations, one give you a sharpener result compared to the other one is less sharp. So you can converge faster by choosing a better metric space. And an extreme case will be here, right? You can Lipschitz constant 1, you really converge really fast. And this is a qualitative difference in the sense they actually convert to different stationary points. So this is a natural gradient example. They have exactly the same objective function, but one of the metric is L2 metric. So DG, one of them is L2, and another is Wasserstein. So you can see on the background, they have exactly the same level set. So because they have the same objective function, so they have the same optimization landscape. But because this different way of choosing gradient, the vector field represent, they have a different way to do the descent. And because they have two different way to descend, if I start with the same starting point, one of them going to a local minimizer, and another one go to the global minimum. So that's where this phenomenon can occur. And I think so far I can only observe it empirically, and I would like to have some proof regarding that line, that by choosing different metric space, you can convert to global minimizer versus convert to a local minimum. But I think that really have to be problem dependent. And that will we'll have to prove that I probably problem by problem. So I hope it, yeah, I'm a little bit over time. So finally, I'm like to draw my conclusion. So the main message of my talk, I want to emphasize that in any optimization framework, as user, you do have these two choices. One is the metric space for the data, and another is the metric space for the parameter. And how to change them, or which will be the best to change them, depend on the particular application. But you do can see and observe those differences quantitatively or qualitatively, changing really your final optimization results. So that's the end of the presentation. Thank you very much.
Okay, thank you for that talk. If anyone is at home and has questions, you can type them into the chat. And if anyone in the room has questions, you can just raise your hand.
Yeah.
So when you're using this HS or SS negative, in practice, how do you do that? You always do go to Fourier space.
That's probably the easiest. You don't have to. You can discrete the Laplacian as well. But the Laplacian people like to do inferior basis.
Yeah, but you have to invert it, so because it's the H minus.
But no, because once you have the, yeah, you have to invert it, but because you can just change the eigenvalue, so the basis doesn't change. So it's the same as you take a digit. You just manipulate the Fourier coefficient. So it's you don't have to invert the whole. You don't invert the Fourier transform, and you only invert the coefficient part.
Okay.
So the f and f Fourier transform and the inverse Fourier transform remain the same. You
So
only
Fourier space is the one we're using, right?
yeah, most of the time. And if it's zero Neumann, so if you are in a bounded domain, it's no longer Fourier anymore. Fourier is only periodic or infinite domain, right? So if you are in a bounded domain, that should be Neumann boundary condition for the elliptic operator. So that's not Fourier transform, but it's discrete cosine transform. So similar thing can happen. Yeah. Okay. Yes. So do you think the frequency principle depends on the architecture of the neural network? Could you design architecture that emphasize high frequencies? That's a very good question. I think it clearly depends on neural network because so far they need assumptions, and one of the assumptions is the neural network to be infinitely wide. And I don't think the other way around is easy to design. Although if the neural network is not infinitely wide, you don't observe such a smoothing property. Yeah.
But does it have to be two-layer or can be multiple-layer?
I think I think they can expand it to multiple layer, but the theorem is going to be not, it's not that clear, but indeed they can expand it to several layers. So the first work was like in 2018 and based on speed in this area. So that I do see results in that direction. Yeah, please.
Go back a couple slides to the images of the two trajectories.
Oh yeah, I like that very much. Yeah, this one, yeah.
Yeah.
Oh,
So
where is that? Okay.
in this, have you seen any other trajectories, how they change with varying norms besides just the Wasserstein norm?
Oh, you can see this. No, you can see this more often. Like say gradient descent, Newton, all give you different vector fields because they are different descent direction anyway, right? You have gradient. Gauss-Newton is preconditioned by J transpose J inverse. Newton is preconditioned by H inverse. So it's all change which direction you go. So in a lot of the practitioners' perspective, sometimes you do observe Newton's method, let's say, convert to one steady state stationary point, gradient convert to the other. It doesn't make any sense in convex optimization. This doesn't occur in convex optimization, but it does occur in non-convex optimization. At the beginning, I remember there's some people comment, oh, this is nonsense. How can you, we know Newton will be faster than gradient descent, but how can you say Newton convert to global minimum, like say gradient convert to local minimum? But nowadays, since you are dealing with such a non-convex optimization landscape, this perspective can no longer apply. I think a more reasonable understanding is to say, each time you change the gradient mechanism, or the descent mechanism, you have a different gradient flow or Hessian flow. And then the baseline of attraction for that flow will change. So for example, this blue one clearly is not in the baseline of attraction for the L2 natural gradient flow, but it to the global minimum. But this point is in the W2 natural gradient flow global baseline of attraction. So in ODE, in the dynamical system, there's notion of baseline of attraction, like when you can convert to, it's similar in that respect, I would say.
My question is more along the lines of, what do these images look like if I choose something else besides L2 or W2?
They will be also different.
Okay.
Yeah, they will be different. I think I choose these two because they look the most different.
Okay.
Yeah, because the one is clearly a linear metric and another comparison so non-linearly. But if you change L2 to, let's say, H1 or H-1, it will be slightly different, but it's not going to be super, super different. Yeah.
Other one is, I think at some point, probably around page 8 or something, you mentioned there is a generalization error. So can you comment?
Yes. So just a second, let me share this version, then I can easily get it. This one, yeah,
right.
So generalization is error is not, I think generalization error is defined in the integral sense for this. So you learn an optimizer based on your data, but then you have a generalization error that is more like they call population loss. Is in the general, there's an integral assuming that your data distribution. So that's how they actually see. Yeah, because for them, like how W looks like or how theta looks like doesn't really make a huge difference. Nobody ever look at the neural network weights and biases anyway. But what you see is like if I throw in a different input, will that be close to the supposed to be the output?
Maybe I have a question about the last theorem in your first part, the resolution analysis. So yeah,
so it's this.
Yeah, this one. I just find it seems that the a priori knowledge about the small m is required, like the smoothness of the m is required in the theorem. So I was wondering what happened if there's no such a priori knowledge of the parameter m.
Yeah, that's a very good question. So if we don't know, so there's like two things. One is you really want to find the one, or you want to find the one that you want, like you have an assumption what you want to. For example, you just want to look for piecewise constant. So that is your prior information, and that already defines which space you are looking for. Or you are looking for up to 5 Hertz frequency, 5 wave numbers. So you already have a subspace. If you do not have a prior or preference in terms of what do you feel like to search, of course, the bigger the better. The bigger the better, but the bigger also the more difficult. So usually people will go the other way around. Instead of searching M, let's say in the entire L2, I'm only searching for like L2 that are punctured by n pieces, so that's a piece one. So you turn an infinite dimensional space to a finite dimensional space. So the infinite dimensional optimization becomes finite dimensional optimization. Yeah.
Thank you.
Are there any other questions? Okay, I don't see any on Zoom, so we can thank the speaker again. Okay, thank you.
Okay.